Hey folks, how's it going? Mr. Mitchell here. In this video we're going to go over paper 1, i.e. the multiple choice questions from the 2017 SQA Higher Physics exam paper. Now there are 20 questions in this section and I recommend that you try them yourself before looking at these solutions. So let's get into it. Question 1 says the graph shows how the velocity of an object varies with time. So you've got velocity in meters per second in the y-axis and time in seconds in the x-axis. It then says the acceleration of the object is. Well, remember we can find acceleration using a velocity time graph, and the rule is that acceleration equals the gradient of the line on a velocity time graph. So notice that we're given some dashed lines here on the graph which correspond to some points on our line. So they're going to be helpful for finding the gradient. So let's choose 2 points on the line of best fit. So we've got x1, y1, which we could make 2, 5, 2 along and 5 up, which is this point here. And we can make point x2, y2, 8, 10, which is the 8 along and 10 up, which is this point here. And to find the gradient, remember we can use the equation from maths, m equals y2 minus y1 over x2 minus x1, or the difference in y over the difference in x. And if we sub in our numbers there, we get 10 minus 5 divided by 8 minus 2. And if you put that into your calculator, you should get an answer of 0.83 meters per second squared, which you can see is the answer A. Question 2 says a block is resting on a horizontal surface. A force of 24 newtons is now applied as shown and the block slides along the surface. So you can see the force of 24 newtons is applied at an angle of 60 degrees to the horizontal. We're told the mass of the block is 20 kilograms and the acceleration of the block is 0.2 meters per second squared. The force of friction acting on the block is. Well, to answer this, first of all, notice that we've got the 24 newtons at an angle of 60 degrees, but that's not very helpful in the way it is just now. So what we're going to do first is find the horizontal component of the force, which we could label FH. So remember this is found from using cosine, cos goes across, so we can say that FH equals 24, the force, times cos 60, which equals 12 newtons once you put it into your calculator. So we could label that on as being 12 newtons there. And remember we're trying to find the force of friction acting on the block, but we're not able to find that until we know what the unbalanced force acting on the block is. So because we've got the mass of the block and the acceleration of the block, we could use F equals ma, i.e. Newton's second law, to find the unbalanced force. So now find the unbalanced force acting on the block using F equals ma. So let's sub in the numbers. We've got 20 times 0.2, which gives us 4 newtons. So assuming the block is moving to the right and there's an unbalanced force of 4 newtons, then this means there must be a difference of 4 newtons between the forward force and the friction force. And we can write the unbalanced force F in terms of the difference between the forward force, which we called FH, and the frictional force F friction. So then to get F friction on its own, we can add that to both sides, and we can therefore just do the 12 newtons minus the unbalanced force of 4 newtons, which gives us 8 newtons. And we can label this in our diagram just to show that that is the 8 newtons there. So you can see the 12 newtons minus the 8 newtons will give the unbalanced force of 4 newtons going to the right. So that means our answer is B. Question 3 says the graph shows how the vertical speed of a skydiver varies with time. So you've got vertical speed on the y-axis against time on the x-axis, and you can then see we've got some labelled parts P, Q, R and S. It then says a student uses information from the graph to make the following statements. Statement 1 says the acceleration of the skydiver is greatest between P and Q. Statement 2, the air resistance acting on the skydiver between Q and R is less than the weight of the skydiver. And lastly, statement 3, the forces acting on the skydiver are balanced between R and S. Which of these statements is or are correct? Well, let's go through each statement in turn and decide which ones are true and which ones are false. So statement 1, the acceleration of the skydiver is greatest between P and Q. Well, looking back at our picture, the vertical speed actually levels off between P and Q, which is actually our first terminal velocity. So the acceleration is not going to be greatest at that point because that's when the vertical forces on the skydiver are balanced, and therefore the vertical speed has become constant. So the acceleration would actually be 0 at that point. So therefore we can say that first statement is false. Statement 2, the air resistance acting on the skydiver between Q and R is less than the weight of the skydiver. Well, looking back at the diagram, between Q and R this time, we've actually got the greatest deceleration, the greatest decrease in vertical speed, and that's because the skydiver has likely opened their parachute at point Q, which has caused a big increase in the air resistance going upwards. So that means that the air resistance going upwards in this case is bigger than the weight going downwards, and that's why the vertical speed has decreased. So therefore the air resistance between Q and R being less than the weight of the skydiver is false because it's the opposite that is true. The air resistance is greater than the weight. And lastly, the forces acting on the skydiver are balanced between R and S. Well, looking back at the diagram again, we can see that between R and S we have reached another constant vertical speed, i.e. the second terminal velocity, which means that the vertical forces acting on the skydiver, which are the air resistance and the weight, will be balanced between these points. So we can say that this third statement is true, which means that 3 only is the only correct one, so that means C is the answer here. Question 4 says a spacecraft is travelling at a constant speed of 2.75 times 10 to the 8 meters per second relative to a planet. A technician on the spacecraft measures the length of the spacecraft as 125 meters. An observer on the planet measures the length of the spacecraft as. Well, notice that this is a length contraction question, and we're told that the technician on the spacecraft measures a length as 125 meters. So that is going to be the proper length L, because the technician is in the frame of reference of the thing that he's measuring, whereas we're asked to find the length as measured by an observer on the planet. So that's going to be L dash or L prime that we need to find. So let's write down our equation for length contraction. L dash or prime equals L times the square root of 1 minus V over C squared. Let's now sub in our numbers to get 125 times the square root of 1 minus 2.75 times 10 to the 8 over 3 times 10 to the 8 squared. And now we can plug all this into your calculator to get an answer of 50 meters, which is the answer B. Question 5 says a galaxy has a recessional velocity of 0.3 c. Hubble's law predicts that the distance between Earth and this galaxy is. Well, for this we need to use our equation for Hubble's law, which is V equals h naught d, and we're trying to find the distance d. So let's rearrange for that to get d equals V over h naught, and we can plug in our numbers. So we've got V is 0.3 times the speed of light c, so that's 0.30 times 3 times 10 to the 8, which you can find on the datasheet, and then divide that by 2.3 times 10 to the minus 18, which is Hubble's constant, again from the datasheet. So putting that into your calculator will give you an answer of 3.9 times 10 to the 25 meters, which you can see as option B. Question 6 says that measurements of the expansion rate of the universe lead to the conclusion that the rate of expansion is increasing. Present theory proposes that this is due to redshift, dark matter, dark energy, the gravitational force, or cosmic microwave background radiation. Well, remember the idea that the universe is expanding and that it's doing so at an accelerating rate, at an increasing rate. That is due to the idea of dark energy, which is the answer C. Question 7 says a student makes the following statements about the radiation emitted by stellar objects. Statement 1 says stellar objects emit radiation over a wide range of frequencies. Statement 2, the peak wavelength of radiation is longer for hotter objects than for cooler objects. And statement 3, at all frequencies, hotter objects emit more radiation per unit surface area per unit time than cooler objects. Which of these statements is or are correct? Well, let's go through each statement in turn and decide which of them are true and which are false. Well, statement 1, first of all, stellar objects emit radiation over a wide range of frequencies. Now remember on the graphs of blackbody radiation curves, which look something like this, where you've got radiation on the y-axis against wavelength on the x-axis, you can see there's radiation emitted over a wide range of wavelengths, which will correspond to a wide range of frequencies as well. So that first statement is true. The second statement there, the peak wavelength of radiation is longer for hotter objects than for cooler objects. Well, if we look at the blackbody radiation curves here, you can see that for higher temperatures, we get these curves that go further and further up on the graph. And if you look at where the peaks are actually shifting towards the left, which is actually going to a smaller wavelength, not a longer wavelength. So the peak wavelengths are getting shorter for hotter objects. So that means that that second statement is false. And lastly, statement 3, at all frequencies, hotter objects emit more radiation per unit surface area per unit time than cooler objects. Well, in this graph, remember the radiation per unit surface area per unit time is given by the area under the curve. So for the hotter objects, the ones with a higher temperature, you'll see that they emit more radiation per unit surface area. So for the hotter objects, you can see that they have more area under their curves, which means that they do emit more radiation per unit surface area per unit time. So that means that statement is true. So this means we have 1 and 3 that are correct, which is the answer D. Question 8 says the following statement represents a nuclear reaction. So we have this element Lr, which is actually lawrencium-256, which goes to nucleus Z plus helium-4, which is an alpha particle. It then says nucleus Z is. Well, remember the rule for nuclear equations, which is the mass number, which is the upper number on the left-hand side, must be conserved, so it must be the same as on the right hand side. And same with the atomic number, which is the lower number, that must also be conserved on both sides. So in this case, because we know it's helium-4 we can start at the end and work backwards. So if we need the mass number to add up to 256 here, if this is 4, then this must be 256 minus the 4, which is 252. And then we need to do the same for the mass number. So if this is 2 and this is 103, then 103 minus 2 gives us 101. But you'll see we have two options with those numbers, 252 and 101, for both A and B, where this one is mendelevium-252 and this one is nobelium-252. So what we need to do is look on the periodic table from the datasheet to see which one of these is actually the correct element. So we have mendelevium, which is the atomic number 101, and nobelium is actually atomic number 102. So this means the nobelium one there is incorrect, so it must be the mendelevium MD. So that is answer A. Question 9 says radiation is instant on a clean zinc plate, causing photoelectrons to be emitted. The source of radiation is replaced with one emitting radiation of a higher frequency. The irradiance of the radiation instant on the plate remains unchanged. Which row in the table shows the effect of this change on the maximum kinetic energy of a photoelectron and the number of photoelectrons emitted per second? Well, for the maximum kinetic energy of the photoelectron, first of all, from the theory, you might remember what increasing frequency does to the maximum kinetic energy of a photoelectron. And the graph looks something like this, where you've got kinetic energy of the photoelectrons against frequency, and above a certain threshold frequency F0, you've got a straight line relationship. So you can see that above the threshold frequency, as frequency increases, the kinetic energy of the photoelectrons increases. So because we've already got photo emission occurring, as frequency is increased, the kinetic energy is just going to continue to increase. So we're looking at either answer C or D here. And then thinking about this one, the number of photoelectrons emitted per second. Now you might be tempted to think back to the theory where we said that if frequency increases, that's going to cause the maximum kinetic energy of the photoelectron to increase, which in turn is going to cause the maximum speed of a photoelectron to increase, and it's going to cause no effect or no change to the number of photoelectrons emitted per second, or the photoelectric current. However, that was the case for when you're only talking about increasing the frequency. But we're told two things in this question. We're told about the frequency and the irradiance. So it's not going to be as simple as just thinking about what was in the theory. So we've replaced the source of radiation, we've now got a higher frequency than before, and we're told that the irradiance remains unchanged, even though we've swapped out the source of radiation. And to think about this, we need the expression for instant photon energy, E equals HF. And there's also another expression for irradiance in terms of this instant photon energy, which is this thing here, I equals NHF. This actually used to be an equation that was learned in the higher physics course for this sort of situation. So we have irradiance I is equal to the number of instant photons times the instant photon energy, so I equals NHF. So we can use this to think about what's happening here. So we can say that if irradiance stays the same and frequency is increased, there must be fewer photons instant on the zinc plate, which carry a higher energy than before. And how do we know that? Well, if we look back at this expression that we've just talked about, we're saying that the irradiance I needs to stay the same, and the frequency has been increased. So if frequency increases, and Planck's constant h is a constant, so that stays the same, then in order for irradiance to stay the same when frequency increases, the number of instant photons must decrease, but we can say that they carry a higher energy than before because there's fewer of them and they need to deliver the same energy. But if there's fewer instant photons on the zinc plate, then that means that the number of photoelectrons emitted each second must decrease as well. Because remember, one photon being absorbed by the plate results in one photoelectron being emitted from the plate. So this means we have increases for the maximum kinetic energy of a photoelectron and decreases for the number of photoelectrons emitted per second. This gives us the answer D. So if you see a question like this again to do with the photoelectric effect, which talks about the frequency and irradiance in the same question, then try and remember this little equation I equals NHF and what the terms stand for, as that can help you work out what happens to the number of photoelectrons emitted each second. Question 10 says ultraviolet radiation of frequency 7.7 times 10 to the 14 Hz is instant on the surface of a metal. Photoelectrons are emitted from the surface of the metal. The maximum kinetic energy of an emitted photoelectron is 2.67 times 10 to the minus 19 joules. The work function of the metal is... Well, notice how we're asked for maximum kinetic energy of an emitted photoelectron, and we're given frequency and asked for work function. So this means we're going to use the equation for the maximum kinetic energy, EK equals HF minus HF naught, and we're asked for the work function, which is this whole term hf0 here. So let's sub in what we're told and try and rearrange for hf0. So we have 2.67 times 10 to the minus 19 for the maximum kinetic energy, and this is equal to Planck's constant h from the datasheet, 6.63 times 10 to the minus 34, times 7.7 times 10 to the 14, which was the instant photon frequency, and this is minus the work function hf0. So if we add hf0 to both sides, then we'll get this expression, and if you put that into your calculator and then subtract this value, you should get hf0 equals 2.44 times 10 to the minus 19 joules, which gives the answer B. Question 11 says a student makes the following statements about waves from coherent sources. Statement 1 is that waves from coherent sources have the same velocity. Statement 2 is that waves from coherent sources have the same wavelength. And lastly, statement 3, waves from coherent sources have a constant phase relationship. Which of these statements is or are correct? Well, let's look through each one and decide whether they are true or false. So for the first one, waves from coherent sources have the same velocity. Well, that is true, and the way I like to remember that is that waves that are coherent will always have the same speed, frequency and wavelength, i.e. the terms in the equation v equals f lambda are all the same for coherent waves. So that takes us to statement 2, waves from coherent sources have the same wavelength. We just said that coherent waves will have the same speed, frequency and wavelength, so that means they'll also have the same wavelength, so that is also true. And lastly, waves from coherent sources have a constant phase relationship. That is also true, and that is one of your learning outcomes from this topic. So that means all three statements are correct, which gives the answer E. Question 12 says a ray of red light passes from a liquid to a transparent solid. The solid and the liquid have the same refractive index for this light. Which row in the table shows what happens to the speed and wavelength of the light as it passes from the liquid into the solid? Well, because the solid and the liquid have the same refractive index for this light, then the red light is not going to be going from a more dense into a less dense material or a less dense into a more dense material. We can assume that the density is the same for these materials. So this means that the speed and wavelength of the light will be unchanged when the light goes from the liquid into the solid. So we should have no change and no change, giving us the answer E. Question 13 says a ray of blue light passes from air into a transparent block as shown. So we've got air and then the transparent block here, and the light comes in and refracts towards the normal. It says the speed of this light in the block is. Well, notice here how we're given some angles, so you should be thinking that we could first find the refractive index of the block by using the angle of incidence and the angle of refraction, and then we can use that refractive index value in the equation for refractive index in terms of speeds. So we've got n equals sine theta 1 over sine theta 2 firstly, where n is the refractive index, theta 1 is the angle in air, and theta 2 is the angle in the material. So plugging in our numbers, we have sine 60 over sine 40, where I used sine 60 for theta 1 because that is your angle of incidence there between the normal and incident ray. And then I used sine 40 because 40 degrees is your angle of refraction there, which is the angle between the refracted ray and the normal. And putting that into your calculator gives an answer of 1.347. I'm not rounding it just now because we're going to use that in a moment. And now we can use our equation for refractive index in terms of the ratio of speeds. So we have n equals v1 over v2, where v1 is the speed of light in air and v2 is the speed of light in the block, which is what we're being asked to find. So let's sub in our numbers. So we have 1.347 equals 3 times 10 to the 8, which is the speed of light in air from the datasheet, divided by v2. And if we rearrange for v2, we get 3 times 10 to the 8 over this number here, which gives us v2 equals 2.23 times 10 to the 8 meters per second, which is the answer D. Question 14 says a student carries out an experiment to investigate how a radiance varies with distance. A small lamp is placed at a distance d away from a light meter. The irradiance I at this distance is displayed on the meter. This measurement is repeated for a range of different distances. The student uses these results to produce the graph shown. So we've got a radiance on the y-axis against 1 over distance squared on the x-axis. It then says the graph indicates that there is a systematic uncertainty in this experiment, and that's shown by the offset from the origin here. It then says which of the following would be most likely to reduce the systematic uncertainty in this experiment. So we have repeating the readings and calculating mean values, replacing the small lamp with a larger lamp, decreasing the brightness of the lamp, repeating the experiment in a darkened room, or increasing the range of distances. Well, if we look at the context of the question, it's all about irradiance, and remember irradiance is the power per unit area, which is sort of to do with the brightness or intensity of light. So if we think about light in this experiment, we're already using a small lamp which can be approximated to a point source, and we want to explain why we might see an offset of readings which all tend towards a higher irradiance value. So this suggests we're getting more light in the experiment than we want to get, so in order to reduce light that might be affecting the experiment, the most sensible answer here would be repeating the experiment in a darkened room. And that suggests that the systematic uncertainty is likely to be caused by the background light level in a room or caused by other experiments in the room. So that means that repeating the experiment in a darkened room is going to be the correct answer here, which is D. Question 15 says a point source of light is 8.00 meters away from a surface. The irradiance due to the point source at the surface is 50.0 milliwatts per meter squared. The point source is now moved to a distance of 12.0 meters from the surface. The irradiance due to the point source at the surface is now. Well, notice how we're dealing with irradiance and distance from a point source, so we want our equation for that first of all, which is I1d1 squared equals I2d2 squared, and we can then sub in the numbers, and we want to find the new irradiance I2. So we've got 50.0 for the initial irradiance, and I'm just going to keep that as milliwatts per meter squared just now, because that's the form that the answers are in here, times 8.00 squared for my initial distance, and that's equal to I2 times 12.0 squared, which was the final distance. So putting that into a calculator and rearranging for I2 gives an answer of I2 equals 22.2 milliwatts per meter squared, which is A. Question 16 says the output from an AC power supply is connected to an oscilloscope. The trace seen on the oscilloscope screen is shown. So we've got two full waves here, and each box on the screen represents a division. It says the Y gain setting on the oscilloscope is 1.0 volts per division. The RMS voltage of the power supply is... Well, to find the RMS voltage, we first need to find the peak voltage using this oscilloscope trace. And remember, the peak voltage is found using the Y gain setting and also the number of divisions for the amplitude of the wave. So we've got 3 divisions that make up the amplitude there. So to get the peak voltage, we do V peak equals 3 divisions times 1.0 volt per division. So remember, the divisions will cancel out, and that gives us 3 times 1.0 volts, which gives us 3.0 volts. And then to find the RMS voltage, we can plug it into the equation relating RMS and peak voltage, which is this one here, VRMS equals V peak over root 2, and substituting in the V peak value, we have 3.0 over root 2, which if you put into your calculator should give you an answer of 2.1 volts, which is option A in this case. Question 17 says a 20 microfarad capacitor is connected to a 12 volt DC supply. The maximum charge stored in the capacitor is... Well, remember, when the capacitor is fully charged, it will reach a potential difference equal to the supply voltage, which is 12 volts. So we can use the relationship between charge, potential difference and capacitance here in order to find the maximum charge. So we have C equals Q over V, and I'm going to rearrange that in terms of the charge Q. So we have Q equals CV, where the capacitance C is 20 microfarads, but let's rewrite that in terms of just farads. So we have 20 times 10 to the minus 6 times 12, and putting that into your calculator should give you an answer of 2.4 times 10 to the minus 4 coulombs, which is option B. Moving on, we have question 18. It says a circuit containing a capacitor is set up as shown. So we've got a 6 volt supply, and then we've got 2 resistors in series, and this creates a potential divider circuit. We've then got a capacitor in parallel with this 120 ohm resistor. It then says the supply has negligible internal resistance, and the maximum energy stored in the capacitor is... Well, in order to find the maximum energy stored in this capacitor, we need to know what the maximum potential difference across it can be. And because the capacitor is in parallel with this 120 ohm resistor, remember in a parallel circuit the voltage across each branch will be the same. So we need to first find what the potential difference is across this lower resistor, and then that will tell us the potential difference across the capacitor. And then we can use an energy equation for capacitors that has potential difference and capacitance in it. So let's think about potential dividers first of all. So we can say firstly that the voltage across the capacitor is equal to the voltage across the 120 ohm resistor. So let's start by labeling the 2 resistors. I'm going to call this one number 1 and this one number 2, which means that if I use the equation for potential dividers where supply voltage is known because I know what that is, so we're trying to find V1 using V1 equals R1 over R1 plus R2 times Vs, and we can now sub in our numbers. So we have 120 for R1 divided by 120 plus 480, which was R2, times the 6.0 supply voltage. And then putting that into your calculator gives us the voltage V1, which is 1.2 volts. And now we know the maximum potential difference across this capacitor is 1.2 volts. So that means we can use this value in an energy equation. So the energy equation for capacitors with voltage and capacitance is E equals a half CV squared. So substituting in the numbers now, we get a half times 30 times 10 to the minus 6, which is microfarads converted into farads, times the 1.2 squared, not forgetting to square that term. We can then put it into your calculator to get an answer of 2.16 times 10 to the minus 5 joules, which is approximately equal to 2.2 times 10 to the minus 5 joules when we round it up, which is answer E. Question 19 says a student makes the following statements about conductors, insulators and semiconductors. Statement 1 says in conductors, the conduction band is completely filled with electrons. Statement 2, in insulators, the gap between the valence band and the conduction band is large. And lastly, statement 3, in semiconductors, increasing the temperature increases the conductivity. Which of these statements is or are correct? Well, let's look at each statement in turn and decide which ones are true or false. So the first one, in conductors, the conduction band is completely filled with electrons. Well, that is false. The reason being that the conduction band needs some space for free electrons to move around in order for conduction to take place. So if the conduction band was completely filled with electrons, then the conductor wouldn't be able to conduct, which kind of defeats the purpose. Statement 2 says in insulators, the gap between the valence band and the conduction band is large. Well, that is true because remember, for insulators at room temperature, the gap between the valence and conduction band is so large that electrons in the valence band can't jump up to the conduction band, and therefore no conduction can take place. And lastly, statement 3, in semiconductors, increasing the temperature increases the conductivity. Well, this is also true, and that's just something to remember. So you can either remember that increasing temperature increases conductivity, or you can remember that increasing temperature reduces the resistance of the material. So that means we have statements 2 and 3 that are correct, which gives us the answer E in this case. Lastly, question 20 is a skills question, and it says that astronomers use the following relationship to determine the distance d to a star. So we have F equals L over 4 pi d squared, and for a particular star the following measurements are recorded. So the apparent brightness F is equal to 4.4 times 10 to the minus 10 watts per meter squared, and the luminosity L equals 6.1 times 10 to the 30 watts. Based on this information, the distance to the star is. Well, remember, in order to answer these questions, we just need to use the equation and plug in the values that we're given, and then make sure there's no prefixes, which there aren't in this case. So to find the distance d, you'll notice we've got a d squared term in the equation, so we're going to have to square root at the end in order to find what the distance d is. But let's just write down the equation and plug in the numbers. So we have F equals L over 4 pi d squared, and substituting in the numbers, we get 4.4 times 10 to the minus 10 equals 6.1 times 10 to the 30 divided by 4 pi d squared, and then I'm going to cross multiply to get the d squared over this side, and if I rearrange, I get d squared equals 1.1 times 10 to the 39. If I then take the square root of both sides to get d on its own, I get d equals 3.3 times 10 to the 19 meters, which is the answer A. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.